Okay guys, so in this video I want to talk about Taylor and Maclaurin series. Now, one of the big things is just for you to know that Taylor series of common functions exists. Because when you get into higher level math, you may not necessarily remember this derivation, but I want to make sure that you remember that they at least exist, so that when your teacher, without any explanation, says, oh yes, and as you know, the series, or for like e to the x is this, or e to the x is just equal to this series, or whatever, then you know what it is that they're talking about, because I can guarantee you they probably won't explain it. At least that was my experience. So it was like, oh, do we know that? That was what I always thought whenever this happened. And so I want to make sure that hopefully that doesn't happen to you. All right, so let's start with a theorem. So this is actually the Taylor Series Theorem. So if f has a power series representation at a, that is, if f of x is the series from n equals 0 to infinity of c sub n x minus a to the n, okay, this is just our generic power series, then its coefficients are given by the formula c sub n, that is our c sub n here, is equal to Fn here. Now this means like derivative. So if it would be F4, that would be like the fourth derivative. So it's the derivative of a over n factorial. And so substituting this c sub n, our coefficient, back into our power series formula, we get the Taylor series formula. So that is to say, if f has a power series expansion at a, then it must be of the form f of x is equal to the sum from n equals 0 to infinity of, again, this derivative of a over n factorial x minus a to the n. So this is the Taylor series. And basically, a, as a reminder, is our center point. So we often center these things at 0. And the Taylor series centered at 0 is called the Maclaurin series. So Taylor series and Maclaurin series are often used interchangeably. Well, actually, we actually hear Taylor series more often to describe Maclaurin series, but Maclaurin series are specifically power series here in this form centered at 0. So instead of x minus a, it's just x, for example. So this series looks like this: a constant, that is f of our center point. So if it's a Maclaurin series, it would be f of 0, because our center point would be 0, plus, but we can center it anywhere we want, plus f prime of 0 over 1 factorial x. So this is the Maclaurin, so again, where a is 0, plus, then we do the second derivative of 0 over 2 factorial x squared, and so on and so forth. So again, this is the Taylor series, and this is the Maclaurin series. But we use those terms somewhat, well, we use Taylor series kind of interchangeably with the two. This could both be described as a Taylor series, since in this case, this is a Taylor series when a is 0. It's just specifically a Maclaurin series as well. Now, one of the challenges of this, which I'm not going to go into, is actually proving that f has a power series expansion. We're just going to take it for granted that we know that these things do have power series expansions and just show how we can write them. Because that aspect is, I would say, most important at this level. And even when you get into higher level math, unless you're proving this theorem, it's really not all that important, I would say, to your general math career, as long as you don't want to go into actually proving this stuff, right? If you're just doing, well, most any other math. Okay, so assuming we have a power series for f of x is equal to e to the x, find its Maclaurin series. Okay, so this is one of those ones where, like I said, when I was a student, I didn't know Taylor series or Maclaurin series. And so, you know, a teacher would just be like, we're dealing with something e to the x, and they're like, oh, well, as you know, this can be written as this series. And it was like, okay. how do I know that? And it'd honestly take about 30 seconds to explain it to a grad level student or even a higher undergrad level student. And yet they don't. So they just move on with their lives, I guess. All right, so I'm going to explain this, how this is found. Okay, so basically we go off of our Taylor series here, but again, where our a is 0. So I'm going to snip this and bring it into the other page so we have it as a reference so you can see this thing while I'm doing it. Okay, so again, this is our Taylor series. So essentially what we need for each of these things are derivatives. So let's go ahead and find these derivatives. We know that f of x is e to the x. That tells us that f prime of x is also going to be e to the x. F double prime of x is also going to be e to the x. F triple prime of x is going to be e to the x, and so on and so forth. Okay, so now let's think about it in terms of 0. F of 0 here would be e to the 0, which is 1. F prime of 0, again, this is our Maclaurin series when a is 0, so f prime of 0 is 1. F double prime of 0 is 1. F triple prime of 0 is 1, and so on and so forth. Okay, so now let's plug this into our Taylor series to get our Maclaurin series. Also, this is referred to sometimes as the Taylor polynomial because it is a polynomial that goes on forever. Okay, so our first term is f of 0, 1, plus f prime of 0, which is 1 over 1 factorial, times x minus 0, so that's just times x, plus f double prime of 0. F double prime of 0 is 1 over 2 factorial, x squared, plus the third derivative at 0, which is 1 over 3 factorial, x cubed, plus 1 over 4 factorial, x fourth, plus 1 over 5 factorial, x fifth, and so on and so forth. I think we can see that pattern. So let's now write this thing as a series starting at 0. So n equals 0 to infinity. All right, we want our first term to be 1. So obviously we want it to be to the n. So let's talk about our x's first. We have x is 0, x to the 0, i.e. 1. So that would need this to be an n. Let's see if it works for other things. When it's the first term, it's x, second squared, third cubed. All right, our x's are taken care of. Now let's take care of the constant. And since every single one of them is like 1, I can just write this all over this thing. So this is like x to the n over the constant now. So this is the only thing that's changing. So the first one is 1. We could call that like 0 factorial. That's 1. 1 factorial is 1. 2 factorial is 2. 3 factorial, and so on and so forth. So that would be n factorial. So this right here is the Taylor series, or the specifically the Maclaurin series of e to the x. This is e to the x. Okay. Now, that's it. That is a Maclaurin series or the Taylor series. If we wanted it in terms of Taylor series, the only difference would be if we wanted it in generic Taylor series, it would be something like well, I guess we would need kind of our derivative here. So I was going to just write the x minus a portion, but that wouldn't have been correct. Okay, so this is what e to the x is when centered at 0. And we could actually see that if we take a look at Desmos here. If we look at e to the x, okay, we have 1 over x over 1 plus x over 1 plus x squared over 2 factorial, which is just 2, plus x cubed over 3 factorial. If you notice, this is definitely looking like a similar shape. And the more we draw this out, so the further out we go, the more this portion, which is either coming down or going up, will get towards the rest of it here. But really, we don't care so much about that since n is starting at 0 and moving on. we really care about like this portion of it getting closer and closer. And so as we take a look at this thing, okay, it's definitely getting closer and closer. So, okay, in fact, I mean that's getting pretty darn good. Okay. And if you notice, this is getting a little bit further out each time, but it's not really going out as much, but it honestly doesn't matter because we're interested over here. But the radius of convergence is actually infinite, is all real numbers essentially. It's like the radius is including everything. So this actually does converge to it as we go out further. But generally speaking, we're really caring about n equals 0 onwards anyway. So anyway, so that is our Maclaurin series for e to the x. Let's take a look at another one. So sine x is another classic one. I've talked about it before, but it's another one that we write as a power series, specifically a Taylor series, or even more specifically, a Maclaurin series. So again, we're going to go off the same thing as before. I'm going to paste this thing in just so we have it as a reference. Okay, so again, what we want to do is we want to take the derivatives. So if we know that f of x is sine x, f prime of x is going to be cosine x, f double prime of x is going to be negative sine x, f triple prime of x is going to be negative cosine x, and f quadruple prime of x is going to be sine x. And so that is where we basically now get some like repetition here. It's sine, cosine, negative cosine, sine, cosine, negative cosine, sine, cosine, and so on and so forth. So let's now think about that in terms of at 0, since it's a Maclaurin series. F of 0 is going to be sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is going to be sine of 0, which is 0. F triple prime of 0 is going to be negative 1. F quadruple prime of 0 is going to be 0. So if you notice, we basically have this pattern now repeating. So 0, 1, 0, negative 1, 0, then it goes 1, 0, negative 1, 0, 1, 0, and so on. Okay? So we're now going to use that and plug these into our formula. So f of 0 is 0. So our first term is actually 0. Plus, so really we'd shift over and avoid that one. F prime of 0, which is 1 over 1 factorial times x. So 1 over 1 factorial x. Plus, now the next one is the second derivative. Second derivative is 0, so it's just going to be 0. Now, the next one here is the third derivative. The third derivative is negative 1 over 3 factorial. So minus 1 over 3 factorial, x to the third. And then we go back to our zeros. So then it would be like plus 0 plus x to the fifth, 1 over 5 factorial, like that. Then it's going to be a plus 0, and then it will be a minus x to the seventh, 1 over 7 factorial. And so basically, if you notice, we have zeros every other term. And so we really don't need them. We're going to shrink this down. This is essentially then x over 1 factorial minus x cubed over 3 factorial plus x fifth over 5 factorial minus x seventh over 7 factorial plus dot 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 dot. Okay, so I think we can see this pattern emerging here. So we're going to start it at 0 again, n equals 0 to infinity. Now we want our first term to have an x. So we can't use n, but maybe we would use like an n plus 1. Okay, now that would work for this first term. 0 plus 1 is 1, but it wouldn't work for the next term because like this is, again, our 0 term. This is 1, 2, 3. So when it's 1, 1 plus 1 is 2. So that's not going to work. So instead, we need to multiply it by 2. So let's double check it still works. 2 times 0 is 0 plus 1. That's going to give us an x. 2 times 1 is 2 plus 1 is 3. All right, that checks out. Let's check it for the second one here. So 2 times 2 is 4 plus 1 is 5. All right, so that's checking out. And then we want to take care of our constants here, and they're following the same form of 1, 3, 5, 7. So we're going to use that same number, 2n plus 1. And then we have an alternating aspect to this. So this would take care of the positive if it's just positive, but it's alternating. So we need to have a negative 1. And our first term needs to be positive. So if we say like n equals 0 would be 1. N equals 1 would be a negative, and so on, so that would work. So this is our Maclaurin series for sine of x. And again, we can check this thing out and see how good this looks to our sine x. Sine x. Okay, so we have our first term. It's x over 1 minus x cubed over 3 factorial. Oh, that's what I forgot to write on my series, sorry. Factorial. Okay, so that's better. Plus x to the 5th over 5 factorial. Okay, if you notice, looking here, I mean, that's looking pretty darn good. It's really, really close to that thing. Okay. And if you notice as well, it's actually working beyond like some radius of say 1. It's going out pretty well. If we take x to the 7th over 7 factorial, it's pushing it out even further. And so this one's radius of convergence is also going to be infinite, much like our e to the x. So we've been dealing with a lot of power series. We tend to have radiuses of close to 1 or something like that, but we can have a radius of convergence that is infinite. And so that is to say, if we take this out infinitely many times, this is exactly sine of x throughout the whole thing, which is pretty impressive that we can force this polynomial to follow this sine wave. Okay, now let's do one more, and let's talk about cosine. So, assuming again we have a power series for f of x equals cosine, let's find its Maclaurin series. Now, we can do the same thing we did on the previous ones, but we can also use a little bit of logic here. If we think about this thing, this is sine x, right? As its Taylor polynomial. So sine of x is equal to this. Now, if we derive sine x, that is, the derivative of sine x is equal to cosine x, then that means that we can derive this series and get cosine x. So let's take a look at that. So the derivative of x over 1 factorial would just be 1 over 1 factorial. The derivative of this next one would be a negative 3x squared over 3 factorial, which if you remember, 3 factorial would be like 3 times 2 factorial. So these 3's cancel. Plus 5x to the 4th over 5 factorial, but we're going to use the same logic, so that is 5 times 4 factorial, minus 7x to the 6th over 7 times 6 factorial, so the 7's cancel. The next one will clearly be a x to the 8th over 8 factorial, minus x to the 10th over 10 factorial. So we can see this pattern emerging. So let's go ahead and write this thing. N equals 0 to infinity. Our first term is 1. So this is like a 1 minus x squared over 2 factorial plus x fourth over 4 factorial minus x6 over 6 factorial, and so on. So we want our first term to be 0, so that means that we're definitely going to have like x to some n. So if we think about this as the first term, or the 0 term, the first, the second, the third, this would work to get this to be a 1. Now let's take a look at it for 2. So when n is 1, that would be 1. So we need it to be a 2n again. So this will ensure that it's going up by 2 each time. Let's make sure it works. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. So that's checking out. Okay. Now let's take care of the number on the bottom, and this time I won't forget the factorial. So it's following the same pattern of 1, 2 factorial, 4 factorial, 6 factorial. So that is to say 2n factorial. Okay. So in this case, let's double check that it works. 0 factorial is 1, so that checks out. 2 factorial, 4 factorial, 6 factorial. Okay, it works out. And then we have a alternating aspect of it, which is -1 to the n. Same thing as the other one. It follows the same signs as sine x. So we have this thing, and this is our Maclaurin series, or our Taylor series centered at centered at 0 for our cosine of x. So this is what cosine x is. Let's take a look at it. All right. So we have 1 minus x squared over 2 factorial, which is just 2. I mean, right away, that's already converging, at least around the origin. Plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on and so forth. And if you notice, this is starting to follow sine. I mean, right here, I mean, it's right on sine. That's really good. And as we pull this out, it follows this curve even more. So that is our Maclaurin series for cosine. So again, the thing I want to talk about in this section is that these things exist, and we have some common ones, which I'm going to go over now, that you should be aware of so that when you get into a higher level math class and your teacher is treating it like everyone knows this statement, you'll be one of the students who knows, hopefully, or at least remembers, like, oh yeah, okay. So we have some important Maclaurin series. We have 1 over 1 minus x. Its radius of convergence is 1. Notice this is just our, like, this looks like the geometric series 1 over 1 minus x, if you recall, that we're just using for our generic power series. Okay. We have our e to the x, which we've already done, and its radius of convergence is infinite, as you notice. The radius of convergence here is 1 because x has to be less than 1. Absolute value x has to be less than 1 for this to converge, since it's a geometric series. Sine x, we can write here. Its radius of convergence is also infinite. Cosine, also infinite. So basically, e to the x, sine x, and cosine x, their radius of convergence is infinite. So this series is exact to it over its whole domain, which is pretty cool. Then we have tangent inverse. Its radius of convergence is only 1, but, you know, we just center it wherever we need it to work. Same thing with this one. The next one, ln 1 plus x, we have this format, which is kind of like a, I mean, realistically speaking, it's the power series x to the n mixed with the harmonic series. So it's like 1/2, 1/3, 1/4. It's an alternating harmonic series along with our powers here. And its radius is 1. Then what we have like the binomial series. This is called the binomial series. We describe k choose n here basically as if it's k choose n, then what that means for us is that we have something like, in our first one it's just k. The next one, when n is like 2, we have k times k minus 1. And then when it's 3, we have times k minus 2. And when it's 4, it'd be k minus 3. That's what this k choose n thing here is, over whatever thing factorial. So that's what this is describing. So this would be the 4. So this would be 4 factorial. So 1, 2, 3, 4, 4 factorial. So this is how we describe this k choose n here in our format. But its radius is 1. This is more of a like probability concept, so it's binomials. Binomials is a probability thing, and so when you get into like a probability class or something like that, then you might see this used a lot. So it's worth noting this one's called the binomial series. Okay, so again, these are our common Maclaurin series, and they can be extended out to be just Taylor series versions of them. These are, as a reminder, Taylor series where we are centered at 0 instead of centering at A. So Taylor series, as a reminder, is just a generic centered anywhere, while Maclaurin is specifically centered at 0, which is kind of the more simplified form. All right, so that has been an introduction to Taylor and Maclaurin series. Again, I want you to be aware of them so that when you move into higher level math classes, it will be familiar, even if you're going to be doing more stuff with it. A lot of times, the thing that was confusing to me was not the rest of the math. It was how did I know that I could write e to the x as x to the n over n factorial? Like, how did I know that? So that's why I wanted to talk about this. Anyway, thanks for watching.